All right, guys, welcome to another episode of CUDA Education. Today, I want to basically go over ray tracing intersection.cpp. The main reason I'm going over this algorithm is because of my confusion with the intersection shader and the hit shader. But I've gotten a little better understanding of what's going on, and I would like to share my understanding with everyone. I've done a couple videos on the ray tracing intersection algorithm. I've done a couple videos with the intersection and hit shader, but I've taken them down and improved it each time. But this time around, I'm like, it's better I just make a whiteboard and kind of discuss the whole algorithm and sort of what's at play. If you guys are interested in installing the algorithm on your Windows-based machine with a Vulkan-capable GPU, check out tutorial number 1, tutorial number 15. Tutorial number 1 is installing the Vulkan API on your Windows-based machine with a Vulkan-capable GPU. And tutorial number 15 is installing all of these examples. Shout out to the author of the examples. It's an excellent script and it's an excellent set of examples. I think personally it's the best way to learn Vulkan. You have running code on your machine and then you proceed from there. There's also the script. There's also ray tracing gems. Those are free ebooks I have linked down below in the description. And they give you a general vocabulary of what is going on as it relates to computer graphics, right? There's a lot of moving parts, a lot of nuance to this thing. I myself am learning, and I take you along for the journey. There's a lot going on with this video. I'm trying to make it as short as possible, but there's a lot going on, and I just ask that you have a little patience and bear with me on this one, because I kind of want to be clear on all the things that I discuss and all the things that I'm going to go through. All right, so it's algorithm ray tracing intersection.cpp, okay? And this is, of course, CUDA Education, okay? So let us go through a couple of things. I'm just going to generally draw what the ray tracing intersection algorithm is about. If you look at my previous videos, it is basically procedurally creating spheres in a scene. And basically those spheres are ray traced so that you know it's an accurate representation of spheres, and it's ray traced, so it's more, the lighting and everything is more accurate and truer than say a non-ray traced version. The algorithm has a light that's like spinning, so because it's spinning you kind of see the shading and all of that stuff as the light is spinning. So it's a ray traced version of spheres, right? So in a nutshell, we have our camera system, and remember our camera is always a sphere, right? It's always a sphere that's shooting out. I'm just gonna do the first half of it, but it's always a sphere that's shooting out rays. Okay, so we have our sphere that's shooting out rays. Okay. Okay. It's shooting out rays into a scene, right? And the scene has a bunch of spheres. So this is a camera. Right? And we're shooting out rays into a scene, and then we have a bunch of spheres, right? And the idea is that these spheres are going to hit some of them, and then some of the, I mean, these rays are going to hit some of the spheres, and then some of the rays are going to miss, right? So some of the rays are going to miss, right? If we take out, 1 second. Right, if we take out actually, let me just draw over the whole thing. All right. All right, let's just start fresh again. Okay, so we have our camera. I'll just make the camera this instead. We have our camera that is shooting rays out. What's going on, guys? What's going on? We have our camera, still no luck. Maybe if I try a different color. All right. We have our camera that's shooting out rays, right? We have our camera that's shooting out rays, and we have, let's say, a couple of spheres, right? So one sphere here and one sphere here, okay? So this is camera. Camera, right? Okay. So some of the rays hit, right? Some of the rays hit, and some of the rays miss. So we'll just say miss, right? Miss. Okay? And then of course, so this is a miss, and this is a miss. Okay? But then some of them, as I said, hit. Okay? So this is pretty much what the application is doing. It's shooting rays into a scene, traversing a scene. We have some spheres that are in the scene, and our rays are basically traversing the scene and seeing what it sees. Okay. That's pretty much what the algorithm is. It's a blob of spheres, and it spins, and there's a light source somewhere that's that's illuminating and not illuminating stuff, but it helps to sort of realistically see the spheres and all that stuff. Okay. That's the simplified version. But there are a lot of things happening behind the scenes. The first thing is that let me try and erase all this stuff now, because so we have our miss rays and we have our hit rays, okay? But things get a little bit more complicated. Just as an effort to clean up sort of the visuals, I'll just get rid of some of these rays, right? Just to clean it up a little bit, all right? So, all right, so we have our camera and we have hits and we have misses, okay? And these are our spheres, right? So this is our sphere and this is our sphere, right? Okay, so we have our sphere, we have our misses, we have our miss rays, and we're hitting some of the spheres. A concept that we really need to discuss is it's a term in computer graphics called BVH, bounding volume hierarchy. All right, so I'll just do it over here, right? So BVH, bounding volume hierarchy. What happens is that when these rays are traversing the scene, we need an efficient way for the GPU to understand or to basically categorize what's happening with the rays, right? Right here we have only two spheres, but in the application, in ray tracing intersection.cpp, in the application, this is not an application that I built, by the way. It's built by a gentleman by the name of Sascha Willems, right? There are 1,024 spheres, okay? So there are 1,024 spheres in the scene, and we have several pixels or rays that are traversing the scene. Thousands of them, probably millions of rays that are traversing the scene. We need an efficient way. We need an efficient way to basically categorize the rays. So are the rays a miss? Are the rays a hit? You want to do it as computationally cheap as possible. This attempt to make it as cheap as possible is where this bounding volume hierarchy term comes in, BVH, bounding volume hierarchy. And what it is it basically is, what it is it puts for this application, it puts it puts a three-dimensional, it puts a box around the sphere, okay? It puts a box around the sphere, so this is a three-dimensional box around our sphere, and we have our sphere inside, all right? So let me, this is our sphere inside, okay? So this is our sphere inside of this three-dimensional box. Okay, now in this specific application, we call this three-dimensional box, we call the box, we call this AABB. All right, so we have AABB, which is the name of this box, right? And we wrap each sphere around, we wrap each sphere with this ABB box, okay? What does ABB stand for? I am running out of space. All right, so we have I don't want to. Okay, so we have AABB. This is called axis aligned bounding box. Okay, that's what AABB stands for. It's an axis aligned bounding box. And then we also have this guy up here that's called bounding volume hierarchy, but I'm not even gonna bother with that. Let's just stick with the axis aligned bounding box. So axis aligned bounding box is actually it's using it's a type of bounding volume hierarchy. Okay, so what's happening is that when a ray traverses the scene, we are give me another color. When a ray traverses the scene, I don't want to use that one. Let me use this color. Or maybe this color. Okay? So when a ray traverses the scene, we don't necessarily want to hit the sphere directly. Why don't we want to hit the sphere directly? We want to hit the axis aligned bounding box. Remember, in computer graphics and ray tracing in general is computationally expensive. Okay? So what that means is that it's a lot of calculations going on. And this is the reason why ray tracing has only recently been available on a consumer level. Like you could go to your local computer store, buy a GPU that is ray tracing capable and can do all this stuff. Back in the olden days, it was only Pixar and DreamWorks and all these big Hollywood studios that had the budget and the hardware to have computers and mainframes and stuff that could do this stuff. When a ray traverses the scene, we want to hit these boxes. We don't want to necessarily hit the spheres directly. We want to hit these boxes first. So think of think of all these spheres that we have as being surrounded by these boxes, okay? And we have our sphere in the middle of it, okay? So we have our sphere in the middle of these boxes. So actually, before the ray hits the sphere, it actually hits the bounding box. And the reason why we do things this way is for a very simple reason. All right? The reason why we do things this way is because we want to differentiate between rays that miss and rays that are in the vicinity of the sphere. So rays that miss, it traversed the scene, we have processing for that. Okay, so we shoot out rays, we traverse the scene, those rays are missed. When we now traverse the scene, we also want to differentiate. We want to differentiate between those missed rays and those rays that are in the vicinity of the sphere. In the vicinity of the sphere. That means it's near a sphere. Okay? It's near a sphere. Okay? So we want to differentiate between the missed rays and the rays that are near a sphere. Okay? Now here is where you guys have to pay attention. There are also rays that are in the vicinity of the sphere, hits the axis aligned bounding box. So the ray traverses the scene, it hits the axis aligned bounding box, but then continues on its way and is still rendered a miss. Okay? So there are rays that are in the vicinity of the sphere, but still miss the sphere. Okay? In the vicinity of the sphere, but it still misses the sphere. This is another complication we have to discuss. Okay? So I'll repeat. We generate a bunch of rays. We need to categorize these rays. And the reason why we want to categorize these rays is because we want to save processing. We don't want to do mathematical calculations that are not absolutely necessary. If you have to do calculations that are wasteful, basically your computer is going to get hot, your GPU is working harder, your computer is going to get hot, you're going to turn on your fan on your computer, and your frame rate is going to drop, right? Because we're not just dealing with 2 spheres, we're dealing with thousands of spheres, right? Especially when you're talking about computer simulation, video games, all that stuff. We're dealing with thousands of this stuff. You don't want to be computationally wasteful. So let's repeat. Rays traverse the scene. We're categorizing missed rays, which are relatively easy to deal with because it's not hitting anything. So it's not like we're rendering or reflecting on anything or anything like that. It's just a miss, right? That's what you call the background scene, the sky model, the clouds, the background color of your application, whatever, right? That's fine. We have to now deal with rays that are in the vicinity of the sphere, okay? So then we have these boxes. Why do we have these boxes? The reason for these boxes is to help us differentiate between the rays that are in the vicinity of the sphere and the rays that are nowhere near a sphere, right? So for the rays that are in the vicinity of the sphere, we do have to do some calculations. Why do we have to do some calculations? We have to do some calculations because we have to figure out, do these rays hit the sphere? So remember, we have our bounding box here. We have our bounding box in the background, and we have our sphere, right? So the sphere is inside of the bounding box. Maybe that's not, maybe I should just color it out. Yeah, I think that's better, right? So we have our sphere inside of our bounding box. Now for the missed rays, easy to deal with. We have to now deal with the rays that are hitting the axis aligned bounding box. So what is the purpose of the axis aligned bounding box? The purpose of the axis aligned bounding box is to decide whether we need to test if those particular rays hit the sphere or not. That is the purpose of the axis aligned bounding boxes. So all of these rays, remember there are multiple rays that are coming through, right? All of these rays that are hitting the axis aligned bounding box, we have to do extra processing, right? For the thousands of rays that are nowhere near an axis aligned bounding box, computationally cheap, right? It's like Goodwill, Salvation Army clothes, right? Dollar store stuff. It's cheap, computationally cheap. But for the rays that are hitting the axis aligned bounding box, it's more computationally expensive. Why is it more computationally expensive? Because we have to now figure out what if a ray hits the axis aligned bounding box, does it also hit the sphere? If it hits the sphere, then that means that we have to do extra processing. But in order to figure out whether we hit the sphere, we have to call what they call the intersection shader. Okay? The intersection shader is a mathematical calculation of the sphere. Okay? So we mathematically now calculate the sphere, and then we see, okay, these rays, these collection of rays have hit the axis aligned bounding box. Let us now mathematically calculate the sphere and see if the ray actually hits the sphere. For these ones, we get a hit. So we get a hit for the axis aligned bounding box, and we get a hit for the sphere, right? And we got to do processing for that. But for all of these rays that are hitting the axis aligned bounding box, we have to call the intersection shader. We have to call the intersection shader, which is mathematically calculating where the sphere is in the scene. This is a very expensive task. This is a very expensive task. The task of mathematically figuring out whether these collection of rays have actually hit the sphere inside of the box is mathematically expensive. Some of the rays that have hit the axis aligned bounding box will ultimately not hit the sphere, right? And it will be computationally less expensive. But for those that hit the sphere, we have to, it's computationally expensive. I mean, for all of these rays, we're calculating whether it hits the sphere. But for the ones that hit, it reflects and all that stuff, and we're able to see the sphere. So the axis aligned bounding box is a very important concept, and it is a child of this bounding volume hierarchy, right? So let me repeat. We have our application. We have our camera system that's shooting rays into a scene. We have rays that miss, it doesn't hit any spheres, and we have rays that come close to a sphere, and we have to differentiate. For the rays that miss, it basically traverses the scene, it goes to the background color. We see the background color of our application. The pixel on our screen, that is where the background is rays that have missed, right? Then we have rays that are in the vicinity of the sphere, and we test to see whether we have to do expensive calculation, because if it hits the axis aligned bounding box, then we now have to call the intersection shader, and the intersection shader is mathematically determining whether this mathematical sphere has been hit by the ray. If it hasn't been hit, it's still considered a miss, but if it does hit, then it hits the sphere, and then we get a reflection, and that's how we get to see that a sphere is there. Let us pause for a second. These axis aligned bounding boxes. What would happen if we made these axis aligned bounding boxes really, really big? Like, let's say we had our sphere. Let's say we had our sphere here. right? So this is our sphere, but we had a huge axis aligned bounding box around it. Yeah, sorry. Yeah, let's say we had a huge. I don't even know what I'm doing. I'm not an artist, guys. I'm not an artist. Yeah, let's say we had a huge axis aligned bounding box around it. Sorry for my drawing, guys. I'm not the greatest artist, right? What if we had a huge axis aligned bounding box around it? Would our application be computationally more efficient or computationally more inefficient? Yeah, I don't even know. And we have our little sphere here, but we have a huge axis aligned bounding box. What would happen? It would be computationally inefficient because all of these rays that are hitting the box, we have to do calculations for. Right? All of these rays that are hitting the box, we have to do calculations for. So we're calling the intersection shader, which is mathematically trying to determine, because you have to generate the sphere and then see where the ray is traversing and see if it hits the sphere. It's going to be computationally inefficient because we have to call the intersection for all of these rays. Now let's do the opposite. Let's do the opposite. Let's say we had. I'm gonna draw the actual. Let's say we had a bounding box that was really tightly wrapped around the sphere, like very tightly wrapped. Tightly wrapped around the sphere, like close. Would it be computationally inefficient or computationally efficient? It would be computationally efficient because for all of these rays, yes, we'll have to call the intersection shader and see if it mathematically hits the sphere and all that stuff. But we only have to do it for 4 rays. On the other example, we did it for way more than 4 rays, right? So this is the purpose of axis aligned bounding box, and this is the purpose of bounding volume hierarchy. Basically, the way how this is explained to me, it's you have a big box and you test that big box with before you start to delve into the shapes inside of the box, because once you hit that big box, then now you have to call all these other shapes inside of your box and figure out whether the rays hit or miss, and that's computationally expensive. All right, so this is at the heart of what this application is doing. This ray tracing intersection example is something. It's what we call these spheres, right? These spheres that we're dealing with. Oh my God. These spheres that we're dealing with are these spheres that we're dealing with are procedurally it's called procedural geometry. Sure, of course. Okay, it's called procedural geometry. Okay, this is a very important word. So the spheres aren't a group of triangles. We haven't pushed a bunch of meshes or 3D models or anything into the application. These spheres are mathematically generated sort of inside of the GPU, and it's a mathematical process. Now, when you look at the application, you're going to see that the edges of the spheres is smooth. You know, it's a very pristine sort of sphere, and that makes sense because we're not building, there's no jagged edges or anything, because we're not building the sphere using triangles. We're building the sphere using a mathematical equation. So the image of the sphere is true to form. You know, we're not trying to basically crazy glue together a sphere using triangles. We're actually just mathematically doing it inside of, I guess, the GPU, right? And this is computationally less expensive because you don't necessarily have to deal with keeping track of all the triangles. You don't necessarily have to deal with memory issues, memory transfer, all that stuff. You basically just organic. Listen, this procedural geometry stuff is like Whole Foods, okay? It's organic food. There's no genetic engineering and all that stuff that's involved in this. It's all naturally done sort of mathematically. And because of that, you could have thousands and thousands of spheres, and it's not computationally as expensive as opposed to if you were making the spheres out of a 3D model or generating it using triangles and all that stuff. It's very, the sphere is very, it's generated very efficiently. But the problem comes in is that in the spatial world of the application, because we're dealing with 3D space now. You can see that when you run the application, or in my previous videos. You're dealing in 3D space now, and you need to make sure that the rays that are traversing the scene, are basically able to be dealt with in an efficient way. Okay, so that's basically what this application is about. I need to discuss a couple other topics. You know, since I have you guys here, I will just proceed. The first question is, what would happen if we didn't have these axis aligned bounding boxes, right? What would happen? How would we generate all of these spheres and sort of see them ray traced and all that stuff if we didn't have these axis aligned bounding boxes? If we didn't have the axis aligned bounding boxes, then if we didn't have these axis aligned bounding boxes, then for every ray, this ray, all of these rays, every ray, this ray, all rays, all millions and millions of rays that are traversing the scene, for every one of them, we would have to call the intersection shader. We would have to call the intersection shader and say, hey, intersection shader, for this ray, did you hit the sphere? For this ray, did you hit the sphere? There would be no way, you know, and we're gonna have way more miss rays than hit rays. But now we're doing an intersection shader call for all of the rays, and that is computationally more expensive, right? You have no way of differentiating rays that are close to a sphere and rays that are not close to a sphere. So especially if you only had like 2 or 3 rays in your scene, 2 or 3 spheres in your scene, it's gonna be, you're calling intersection shaders for all million rays that are in your scene, when you only have like 2 spheres in your scene, and the rays associated with those spheres or in the vicinity of those spheres that you have to call the intersection shader for. So again, if it's computationally expensive, that means you're working your GPU harder. If you're on a laptop, you're burning up more electricity. You're probably, because you're burning up so much electricity and you're working your GPU hard, your laptop is probably running hot, and it's probably scorching you if your laptop is on your lap, right? Which means you're turning on your fan. So, which means your battery is dying, because you're doing all these calculations, you're turning on your fan, you're generating all this heat, your application is running slower, which means you probably have to run it a longer time to see what exactly is going on, because the frame rate is so low and it's probably jagged and stuff. All of these things are a result of your application being inefficient, because you're now trying to mathematically calculate whether a sphere hits all rays, and you don't want that. You want to differentiate between miss rays and rays that are in the vicinity of the sphere, so that you can, just do the intersect shader calculations for those that are in the vicinity of the sphere. Okay. There are more things we have to discuss, so I'm just gonna get rid of these things for now, but we do have I'll just move the miss, because we kind of, so we have our miss guy up here, right? So you guys know that there is a miss, right? So we have our miss up here. I hope you could see it. I think you can. Okay, so we have our miss ray up there. All right. A couple other things that we have to discuss. So we have shaders, right? Let me just do it in a more fun. We have shaders, right? Okay. So we have shaders. Come on, work with me. All right, we have shaders. Okay, so we have a ray gen shader. We have a miss shader. We have a hit shader, and we have our intersection shader. Okay, I butchered that one. Okay, maybe if I do this. All right. Okay, so we have a ray gen, miss, hit, and intersection shader. Now, when I was investigating this application, I had a hard time figuring out what's the difference between the hit and the intersection shader. Now, in other ray tracing examples in the solution set that we have from Sascha Willems, in other ray tracing examples, for ray tracing applications where you're not procedurally generating, it's not procedural geometry, you're not mathematically creating these spheres, we don't have an intersection shader, right? And of course, me being me, I'm like, why don't we have what is this intersection shader? Why do we have to have this intersection shader? All the other ray tracing applications doesn't have this intersection shader. I need to know the difference between an intersection shader and a hit shader. And a shader, in my personal estimation and definition, it's a nugget of processing. It's a nugget of processing that you either call or don't call. Okay, that's, don't get hung up on these things, but it's a nugget of processing that it's either you call it or you don't call it, depending on what's happening in your application. Okay, the ray gen is pretty simple. We're generating rays in our scene, right? So we're generating rays in our scene, and things happen to those rays. That's the ray gen. The miss shader is, we generated a ray into our scene, the ray did not hit anything, what happens next? So in our application, this mist shader basically says, okay, make the background color of our application black, or make the background color of our application blue, the color blue, or make it the color green or red or orange, whatever you want it to be. It's a very simple thing, which is why every time I say the rays miss, we don't really have to worry about it too much. It generates the color for that pixel because the ray basically traversed the scene. It didn't hit anything, so we use our sky model or background color, whatever, right? Also for this guy up here. Okay? Now we get into the hit and the intersection shader. All right, so the hit shader, I want to make sure I'm not confusing them and all that stuff. The intersection shader, the intersection shader is actually what records, and this is where things get a little confusing. The intersection shader is what mathematically calculates the sphere and tells Vulkan and the world that be and the powers that be that, hey, this ray has hit the sphere. Okay? So in order for the intersection shader to know whether a ray hit the sphere, it has to generate the sphere mathematically, right? So because it has to generate the sphere, it's computationally expensive because you have to mathematically generate the sphere, and then you have to mathematically see where the trajectory of the ray is and whether the sphere and the trajectory of the ray collides. If they collide, then we what is called record a hit. Okay? So that is what the intersection shader does. When a hit is recorded and the intersection shader says, okay, okay, my friend, intersection, yes, then we call the hit shader. Okay? We have an intersection. So what happens is that intersection shader now, it says yes, an intersection has occurred. And then what the hit shader does, the hit shader is the one that actually, the hit shader is the painter. So the hit shader is the one that actually paints the sphere, makes the sphere nice and round, make sure the lighting and all that good stuff so that we could visually see the sphere. Okay? This is how I understand it. This is how it's been explained to me. And that's how I'm rolling with it. So the hit shader is the sphere. I mean, the hit shader is the painter. It's what actually visually you're able to see the sphere. Okay? But the real processing is the intersection shader, because before you get to the hit stuff, you have to, the hit shader, you have to know if the ray mathematically hit the sphere, right? So this is the expensive guy. I mean, this, you know, the hit shader is what is the painter, but the intersection shader is what makes everything go. Right? It's sort of the heart of this application. So this is how I was able, and trust me, I made like 2 or 3 videos, you know, trying to decipher the difference between the two. I asked the powers that be and they gave me like a 1-sentence answer, right? That's what the relationship between the hit and you know, it's kind of confusing because I'm saying hit here, but then I'm calling these hits and stuff, but let's just separate the two. Rays traverse a scene. We have to test whether the we have to differentiate between rays that miss and rays that are in the vicinity of the sphere. For the rays that are in the vicinity of the sphere, we use the intersection shader to test whether that ray hit the sphere. If the ray hit the sphere, then we call the hit shader to paint and visually show that there is a sphere in our scene. Okay? So it's basically, rays are like pixels in your application. So each pixel is a ray in your application. So you have your computer monitor and you have about 1 million pixels, right? For you 4K guys and all this new technology stuff, computer monitor stuff, right? You got like 1 million pixels going on your monitor. You need to decide what happens with each one of those pixels. So a pixel is like a ray. If the pixel is part of, if the pixel or the ray is part of the sphere, you're going to paint a sphere, right? But you have to test whether it's part of the sphere or whether that pixel is part of the sphere by the intersection shader. Okay, so that is our hit shader and our intersection shader. Now I have a question. Let us say I don't want to do spheres anymore. I don't want to do spheres. I don't want to see spheres in my application. I want to see cones. Okay? Or I want to see donuts in my application. So we're done with spheres now. We're trying to look and see if they're donuts. Okay? What happens next? If we're trying to see donuts, how do we change our application in order to see donuts or to see cones or to see squares? What do we have to change? The only thing we have to change is this guy here. Right? And I will make a video. I have a previous video, but I took it down because I need to explain this stuff a little bit more clearly. But the only thing you have to change is this intersection shader, because remember guys, the intersection shader is what decides what shape we're mathematically calculating. The intersection shader is what decides what shape we're mathematically calculating, and therefore what shape we hit when our rays traverse the scene. The only modification we have to make is changing the calculations in the intersection shader. So we're not calculating a sphere anymore, we're calculating a cone, or we're calculating a donut, or we're calculating a square, right? We have to change this guy, right? And if you fundamentally sort of guess that correctly, then you sort of are on the right path of what this is all about. It's when I make the change, when I change the shape in the application, it's a rough thing, because you kind of have to change other things too in order for it to look nice and fuzzy and stuff, because if you're doing a different shape, you kind of have to, if you want to make it really nice, like Pixar level nice, you're gonna have to change the dimensions of the bounding box, because these, the dimensions of the axis aligned bounding box and all that stuff. Because remember, these bounding boxes are sort of, the size of them are determined by the radius of the sphere that we're dealing with. Okay, so the size of the bounding box is determined by the radius of the sphere. If you start changing the object inside of the if you start changing the object inside of the box, then the object, it's not going to align properly, and it kind of gets a little messy, but that's a topic for another day. We also algorithmically in the ray tracing algorithm, we associate each axis aligned bounding box with a specific sphere. So it's not like we hit an axis aligned bounding box and then we have to guess which one of the spheres in our scene we have to mathematically calculate. It's sort of the same index that's used for the bounding box is the same index that's used for that individual sphere. All right. What else did I have? I had some other things that I wanted to discuss. Another thing that I sort of, just as a thought experiment, right? Another thought experiment that I had, and I hope I can explain it properly. Another thought experiment that I have was like, okay, if we have a bunch of spheres, right? If we have a bunch of spheres, right? If we have a bunch of spheres, why not just have one big bounding box around all of the spheres, right? But why not just have one, but this is when I didn't really understand the purpose of the axis aligned bounding box, right? Why not just have one big, for all 1,000 spheres, why not just have one big axis aligned bounding box, since apparently we need bounding boxes to see the spheres, right? It doesn't make sense to do this because once you do a hit on the bounding box, now you're gonna have to calculate all these spheres. Every time you do a hit on the bounding box, you're gonna have to mathematically calculate all these spheres inside of the bounding box and test whether the ray hits any one of these multiple spheres inside of the bounding box, right? So it just doesn't mathematically make sense, right? Because you're not really achieving anything with that, okay? But that was when I didn't really fully understand axis aligned bounding boxes, right? So that was one thing. One thing that that was a thought experiment, but I kind of figured out that that we didn't need to, it doesn't computationally make sense. All right, the other thing that I wanted to discuss is that apparently in computer graphics world, in this ray tracing world, at least with the Vulkan API, the Vulkan API cannot inherently or implicitly see procedural geometry. So it's not like I could just have a sphere, that's procedurally generated, meaning the equation of a sphere, and just shoot rays into the scene and expect that the rays are gonna see the sphere, right? It doesn't really work that way. I don't know the backstory, I don't know the intrigue and the gossip and the soap opera behind it, but I just know that if you mathematically generate an object in your scene, you can't just shoot rays into the scene and expect that Vulkan is gonna see that an object is in the scene, right? Which is why, again, we have this intersection shader where every time a ray is in the vicinity of a sphere, we have to call the intersection shader to mathematically generate the sphere and then mathematically see if the trajectory of the ray is going to hit that sphere, right? I don't really have the I don't really have the full background story on why that is, but I know that it's a thing. All right. Another thing is that in Vulkan, and it's basically because I was tinkering with the code and all that stuff. Apparently in Vulkan, it's really hard. I don't even know if I want to say this because it might be confusing, but apparently, like, you know, when a ray hits something, it's really hard for Vulkan to, like, if it hits something but then it continues, like if it hits an object but then you want the ray to continue, it's really hard for Vulkan to deal with. Okay, it hit the first object, but I want the ray to continue through the object, and then it hits a second object. Like, I don't know, Vulkan doesn't deal with like 2 hits on a particular, like 2 hits of an object on a particular ray well. These access aligned bounding boxes are not objects. They're sort of an imaginary, almost like a wireframe kind of thing. So, you know, when we say we hit the access aligned bounding box, we're not actually hitting an object. So it doesn't really mess up with that concept that I just talked about, where, you know, you hit one object, but then the ray continues and it hits a second object. Like, it doesn't count here because the access aligned bounding box isn't technically an object. So you're just basically, you know, trying to see if, well, you know, because it's not an object, it's the reason I know this is because I tried to rebuild the application where I could visually see the access aligned bounding box around the sphere, but it got messy, and like I had to do like 2 bottom level acceleration structures, one for the spheres and one for the bounding box and stuff, because now I'm trying to make the bounding box a visual object in the application, and it gets messy. So, you know, that's a topic for another day. So we talked about bounding volume hierarchy. This bounding volume hierarchy stuff is why we have this thing called acceleration structures, right? So, you know, you want to sort of make your application more efficient. That's where this acceleration structure stuff in ray tracing comes in. I don't want to belabor that point though. That's pretty much all I have for this. So thank you guys for watching. Again, tutorial number 1 to install the Vulkan API on a Windows-based machine with a Vulkan-capable GPU. Tutorial number 15 to install all of these examples on your machine. I walk you through the process of doing that. Thank you to Sascha Willems for creating this wonderful application. It's really helpful in helping us understand Vulkan, because there's just a lot of stuff going on all at once. And we really need many examples just to see, you know, what is what and why things are. I'm slowly understanding all the moving pieces of Vulkan, and why shader binding tables are important, and why shaders are important, and why, you know, we need access aligned bounding boxes, and you know, the difference between a real object that's like passed in as a 3D model or a mesh, and then a procedural geometry object and all that stuff. So thank you to the powers that be. Please, guys, work on this stuff. Tell your friends about it. This is the way of the future. You know, play video games, but also learn how to create them and create other things. The world is increasingly becoming digital. You know all that good stuff already. So, you know, take some time to learn this stuff. Get some of your friends together and learn it together. It's time well spent. All right, guys. Thank you for watching. Have a great day.